So E. coli naturally produces hydrogen gas as it grows under fermentative conditions. So it's a very flexible bacterium, can grow under aerobic conditions, doesn't produce any gas, a bit of CO2. When you switch it to anaerobic conditions with glucose, as if you were using yeast to ferment something, the E. coli will ferment as well. But it produces lots of formic acid, and that formic acid can then be turned into CO2 and hydrogen. And so you could imagine that any waste stream such as food waste or agricultural waste that produces cellulose or other substance sugary can be fermented by E. coli to produce hydrogen, and that could be a great clean fuel for the future.
Danger, danger, high voltage.
So there's a really cool invention called a proton electrochemical membrane, or a proton electrolyte membrane, and that allows you to generate electricity in something called a fuel cell. So the electrodes, there's a cathode and an anode. The anode will react with hydrogen gas, and if that's made of a precious metal like palladium or platinum, split the hydrogen to protons and electrons. The protons can then move through this membrane, proton electrolyte membrane. So it operates like a battery in reverse, and protons go through and react at the other electrode with oxygen, and you get water. But the electrons can't move through this electrode, they have to move around the wire to the other side, so you get electron flow, and when you get electron flow you get electricity. So if you can make one of these things with a special membrane and with two precious metal electrodes, you can use hydrogen gas or biohydrogen produced by bacteria, convert that into electricity. It's quite easy to make mutants in E. coli actually. So way back in the 1940s and 50s, E. coli was chosen because it's very fast growing, it's non-pathogenic, in this new field of molecular biology. And very rapidly scientists realised that you could transform E. coli easily, so you could put DNA into it, and they found that you could modify the genome easily. And that's because if you put a piece of DNA that has a sequence that's very similar to the chromosomal sequence, there are special proteins in the bacterial cytoplasm that will recognise that, and it will switch in that similar DNA into the E. coli chromosome. It's called homologous recombination. So if you put in a piece of DNA that looks pretty much identical but it's changed just a tiny little bit, the bacteria will think, oh, that's my DNA, I'll put it into my chromosome. But at the same time, what it doesn't realise, it's moved in a little change, a little mutation here and there. It can actually convince E. coli to delete whole genes by just persuading it that this is the right thing to do. So you take a little bit of clever black magic, but you can delete one gene, you can delete two. I think in this paper it deleted up to 7 or 8, I think, in one strain. When it comes to bioenergy and renewable energy, you just want to minimise waste, and you want to find ways of using every single scrap of biology and every single scrap of industrial waste to generate more energy. So the idea here is that you could engineer a bacterium to produce hydrogen, produce more hydrogen. Okay, so then you could take food waste and you could sprinkle in your engineered E. coli and it would produce hydrogen gas. Then you want to produce electricity from that. Then now you've got a problem, because if you make a fuel cell, you make it out of precious metal, and that costs a lot of money. So what we discovered in this paper was that if you take a different E. coli strain that's been engineered a different way, you could mix it with crushed up catalytic converters, which contain palladium oxide that's normally thrown away, and you could pump some of that biohydrogen that you produce from the food waste into this, and those bacteria will take that hydrogen gas and use it as an energy source to reduce the palladium oxide back to palladium metal. And those palladium metal nanoparticles form on the surface of this bacterium. Then it dies and it falls to the bottom. But then you can harvest that, so then you've got nanoparticles of palladium. and you can paint that onto a plastic sheet and make a bioelectrode from that. So then you can take your vat of food waste, sprinkle in your bacteria, produce hydrogen, and you could make electricity from a fuel cell that's been made by bacteria using bio-nanoparticles that come from your crushed up catalytic converters. So then you start to get this whole cyclical process that everything's renewable, everything's sort of biologically based, and we're using waste catalytic converters to make a fuel cell. We use waste food products to make the hydrogen. It's done by engineered bacteria. So you can really save a lot of money and generate electricity that way. And actually the biopalladium nanoparticles that we generate much more efficient at producing electricity in a fuel cell than chemically produced particles of precious metal are. So with this type of biotechnology, the scientist always wants to be in control.
Yeah.
So there are natural strains that produce hydrogen gas, but they're not easy to genetically modify. They're not easy to work with. With this one, we want to exert some control, so we can make mutants, we can upregulate some genes, we can downregulate some other ones, and that's really important to have control, especially when you're working with GM organisms. So you can even imagine if you're worried about this thing being set free in the environment, you could engineer in what's called a kill switch, so it could kill itself if it escaped. So it's all about control. With a natural system, it's all technology. Anaerobic digesters are all over the world. Just mix some stuff together and produce some gas. Not really, but we continue to work on this. So what we're doing now is we're taking more of a synthetic biology approach, and we've looked at the enzymes in some of the natural strains that you alluded to that produce lots of hydrogen under different conditions, and we're trying to engineer those enzymes into E.Coli. So you can make a strain that produces lots of different types of hydrogenase enzyme, not just FHL, and can take electrons from lots of different pathways, and hopefully that will boost hydrogen production in this sort of new synthetic strain. The big picture, this is obviously it's going to save the planet in the long term.
Yeah.
We'll all be driving hydrogen fuel cell cars, and there'll be no need for fossil fuel probably in the next 3 or 4 months. Seriously, it's going to be years that go by, because it's very, very difficult to break people's habits, to try and make a breakthrough in renewable energy. But that's what being a university scientist is all about, because we're not driven by profit, we're not driven by the short term. We can develop and we can research and we can find out new scientific solutions that maybe in 3 months, but maybe in 50 years will be more useful to people. Don't be an academic if you want to be rich.